In their beginning, there was the first law, and then there were PV graphs. And it was good. Okay, so what we're talking about here is the idea of the first law of thermodynamics and how we're going to take that, either in this video or the next one, I don't know yet, we'll see where we get, to these PV graphs. Now, if you haven't seen our prior video on the 3 laws of thermodynamics, go watch that now. Because what you should know already is that the first law of thermodynamics, which is not really the first law, but whatever, is this delta U equals some Q plus W, where delta U is really a change in internal energy with my scrawly handwriting. So it's a change in internal energy. We know it as the equation 3/2 nR delta T, or if you wanted to write it, 3/2 N K delta T. And also recall, and this is where things get so complicated within this unit, that this 3/2 only exists for monatomic elements. If you have a diatomic element, like those nitrogens and oxygens and whatnot, then that 3/2 is going to become a 5/2 because there's more degrees of freedom. Our Q value here, Q is some amount of heat added or taken away from the system. So it's just heat added or lost in the system or to the system. And then our last term here, this W, it simply means work, and it is work either done, it's either done onto the system, or it is work done by the system. Okay? Work done on the system, we're going to say is positive. Work done by the system, we're going to say is negative. In a similar light, heat added to the system is positive. Heat taken away is negative. So a negative Q means you lost heat. Plus is a gain. So that was our first law of thermodynamics. Now, how can we start thinking about this into a system that we might be somewhat familiar with this, and what are some other terms that we might need to know? Well, let's think for a second about a can. We have a can here, or a barrel, whatever you'd like to call it. And let's put on the inside of it a floating lid. What I mean by a floating lid is that this lid is able to like float up or down depending on the conditions of the inside of our container. So it's a floating lid. And I'll try to be a great drawer. There it is. Now, we put something like an ideal gas on the inside of this container. And because this lid can float, if the pressures were very high or high enough in this container, in this vessel, it could push this lid upward. There would be like an upward acting force over the area. It would cause the lid to rise. If for some reason the lid was heavier than the internal pressure of that gas, the lid would fall down. Once they equalize, it gets to some point and it stops, right? But what we can say is this. If this lid is being pushed up, it's going to arise to some new height. When it arises to some new height, there is more volume on the inside for these gas particles to move around. As a result of this, we can think that this system, it had some pressure, it had some energy stored inside of it. When it pushed that lid up, it did work on the lid. it pushed the lid to a higher gravitational potential. If the gas did work, that means the gas lost energy. Which means if the gas lost energy, if its delta U had to be a negative number, and let's pretend in this case that there was no heat added or subtracted from the system, that means this work here has to be a negative number, which means the work was negative. This is the system doing work. When the system did work, it used its own stored internal energy to do that work. So the system lost energy. That's what we're talking about there. On the flip side, if you took your hand, which will be crudely drawn in a purple fashion here, if you took your hand and you pushed down on this lid and you like compressed that gas, you would be doing work on the gas. You would be doing work. This system would gain an internal energy, which means the work needs to be a positive value. So positive works are works that are done on the system. Negative works is the system doing something, because that internal energy has to drop. Okay? Those are important things to think about within this system here. Now, given the fact that I could have this floating can, and maybe the can lid gets stuck at some point, so that no more work's allowed to be done at all, I can still change internal energies by heating or cooling this can. Because remember, in these equations that we just wrote up here, we kind of ignored the whole heat factor for a second. But I can take a blowtorch to the can and heat up that gas, or I could take that can and stick it in a bucket of ice water and cool that gas down, and also change internal temperatures. So let's talk about some various scenarios that we could have in terms of thermodynamics. So our first thing that we can have is something known as an isochoric change. An isochoric, also known as an isovolumetric, that will be like the new school way of saying it. The old school way that many of your Russian professors in college will use will be isochoric, because it is the classical physics name, is the idea that a volume is constant. If you have an isochoric scenario, your volume is constant. This is like the can of beans. We can also have an isothermal. Once again, this iso comes up. Iso meaning singular or one. Oftentimes in sports, if you run an iso play, it's like an isolation play, meaning one. So this is one. When we think of thermal, we think of temperatures. So this is one temperature, meaning that the temp is constant. So an isochoric has a constant volume, an isothermal has a constant temperature. We also have an isobaric, which if you think about a barometer or bars, if you're measuring in that weird unit from chemistry, that's a measurement of pressure. Pressure. And spelling is nice. And what's this? Is Dylan here. So we've got Dylan now. So we've got isobaric, which is the pressure is a constant. And we also have something a little bit weird, and we're going to talk about this much later on because it's like kind of different. Something known as an adiabatic, which is no heat. Or really, there's no heat transfer here, okay? So an adiabat or an adiabatic is kind of a weird thermodynamic process of these four thermodynamic processes: the isochoric, also known as the isovolumetric, the isothermal, the isobaric, and the adiabatic. These are all thermodynamic processes which obey the first law of thermodynamics, each one having their own little features here, okay? So what can we do with this? What's going on here? One final note. In adiabat, they normally happen very fast. These happen fast. They have to really happen fast. If they happen slow, you, due to Newton's law of cooling, have a lot of heat transfer that can exist. So if they happen quickly, no heat can get in, no heat can get out. It just happened. So something to keep in mind. But where can we go with these ideas? Well, let's come back to our floating can lid. And let's start working through this idea of work, because we know that we've got some work going on here to either raise the can lid from internal energies or to compress it with some external energy. So let's go back and let's start looking at the idea of work. We know from last year, or from prior physics knowledge, that work is equal to a force dotted to a displacement. And you could write this as delta x or d. It doesn't really matter. It is just some displacement here. Technically, we know that there is a cosine here, but let's assume that the parallel components are the entirety of these force vectors and the displacement vectors, so that theta equals 0 here, so we don't have to worry about that cosine. And basically, what this implies for us is that this force, which we could say is due to the gas, this red force right here that we drew initially, this is that gas force. That force is in the direction of the distance this moves, which is up, or rather the displacement it moves, which is up. So they're in the same direction. What we can say then is that let's pretend that instead of looking from the start to the finish for this entire delta D, let's just look at a tiny piece of it, some like small piece of it here, and we'll just call it delta L. We could have called it delta D, we could have called it delta X, whatever, it doesn't really matter. Let's just call it delta L. That's how I have it written. So the work done by the gas is equal to the force from the gas multiplied by some delta L. Well, why does this matter at all? And why did we choose a delta L? Well, we know that this force done by the gas, we can equate this to the pressure of the gas multiplied by the cross-sectional area of that lid. And what this means is when we say that this work done by the gas is equal to the pressure of the gas multiplied by the cross-sectional area in delta L, we knew from our study of fluids that a cross-sectional area multiplied by some length is a volume. So if we're just taking a small bit of that length, this is really saying a work is equal to a pressure multiplied by a change in volume. So we can say that the work done via the gas is equal to some pressure of the gas multiplied by a delta V. This is a brilliant idea, because we already know that PV equaled nRT. Now we know that P delta V equals nR delta T. Basically, if the gas is changing its volume, it is either doing work, if it's expanding, or if it's collapsing or contracting, something has to cause that, then it would be having work done on it. Okay? Generally speaking, if delta V is positive, work is negative. Because that's the system did work. It expanded, that gas pushed the lid up, or it blew the system up, had to do some work. If delta V is negative, work is positive. In some textbooks, this convention may be backwards. That's because in some textbooks, they won't write the first law as Q plus W. They'll write it as Q minus W, and then they'll say if a gas is expanding, that's negative work, or that's positive work. Yeah. I don't like thinking about it like that. I think it doesn't make any sense. If the gas does some work here, that internal energy needs to be negative. Let's make the work a negative quantity. So that physically makes sense in terms of that math. There's no extra negatives to carry around or just like pretend they're there. That way works out the best. Okay? Note this equation as well. This equation is actually one of our 4 thermodynamic processes. This equation here is isobaric. The pressure is constant. But it gives us a really interesting idea here. And this is an idea that's going to come up in our next video when we start talking about how to use graphs here. If I have some pressure and a volume, what we're really doing here in this P times delta V is we're really saying if I have a pressure and I go through some volume, I want to multiply them together, which is really finding an area. So even though this equation for an isobar or an isobaric P delta V works, it gives us a really fascinating idea of we need to start looking at a PV or a pressure volume graph, and we need to start looking at the areas underneath curves, which if you're doing anything with calculus, there might be some integration in your future. But for now, that's where we're going to hold up on this. If you're more curious about these PV graphs, that will pop up in our next video. But until then, adios, and take it easy.